Hello class, this is Christian and the modern physics topic I chose to present to you guys today is about the discovery and use of lasers. Laser is in fact an acronym that stands for light amplification by stimulated emission of radiation. Basically, it means that lasers are optical devices that amplify light waves through stimulated emission. They were discovered in 1960 by Mayman, who built the first one, also called ruby laser. Ruby laser will be discussed later in the presentation. Following the ruby laser's discovery, Jevon and Associates came up with the first gas laser using helium and neon gases. Other scientists picked up on that and came up with innovative and revolutionary design and purposes for laser. Laser light has characteristics and the following four are responsible for its properties. We have intensity, directionality, monochromaticity, and coherence. The high intensity of light produced by laser is due to the coherence nature of laser light, which enables it to focus over a really small area. Laser light has a high directionality also because the beam produced by the device is very strong and concentrated. While ordinary light, for example, emits light in all possible directions, laser light travels as a parallel beam over a long distance without spreading. Laser light also has a high monochromaticity because every specific type of laser can only produce a light of predetermined color, as the laser light is concentrated and narrow and has very narrow range of wavelengths where that can be used for a specific device. Finally, laser light is coherent because all emitted photons bear a constant phase relationship with each other in both time and phase. Additionally, the wavelengths are identical in phase and direction, forming coherent waves. The takeaway is that laser light is so powerful and capable of propagating over longer distance and not easily absorbed by water, and that makes it 100 times better than ordinary light at focusing. Now to expand on the physics behind lasers. How do lasers do in fact work? The principle through which lasers function is based on the process of stimulated emission from Einstein's quantum theory of stimulation of radiation. Basically, atoms absorb energy which results in the electrons being excited to higher Big-Quant energy shells. This process is called pumping and consists of producing population inversion in the atom in the medium, meaning more electrons or atoms are in the excited state than there are atoms or electrons in the ground state. Pumping of electrons to a higher energy state can be done three different ways. We can do optical pumping, electrical pumping, or we can do direct conversion. In optical pumping, electrons or atoms are excited by an external optical source like a laser, while in electrical pumping, the electron accelerated to a high velocity by a strong electric field, and follow that, there is a cohesion between the neutral gas in the device and ionization of the medium, and that ionization causes the electron to go to a higher energy level. CO2 lasers are examples of lasers that uses that type of pumping. Finally, direct conversion of electron is where we use electric energy and convert it directly to light using a semiconductor laser. Then the electron are triggered or stimulated by an incoming photon with the specific energy to emit photons that in phase have the same direction, the same wavelength as incident photon, resulting in a beam of laser light. The rate of stimulated emission of radiation is proportional to the population at the higher energy level and to the density of the incident photon. As the laser beam is emitted, that can be done either as a continuous beam or in a pulse fashion. Pulse lasers are important for precision micromachining of various materials, and continuous wave lasers are important in medicine. There are two different types of pulse mode lasers or pulse wave. We can have quasi-continuous mode or gated pulse mode, and we can have the free running pulse mode. In gated pulse mode, the laser light is periodic on and off by a mechanical shutter in front of a continuous wave laser at the duration of a few milliseconds, and for the free-running pulse mode, the high energy of a laser is emitted by for a few microseconds, followed by a reflective long period gap controlled by a computer. Continuous wave just consists of a beam being emitted at one power level, continuous as the foot switch is pressed. For either one of them, the power average of the continuous mode does not vary. It will stay the same throughout, and for the same duration, pulse mode lasers will also have the same average as the continuous lasers. The only difference is that pulse lasers will have peak where the intensity or the power of the light being emitted is way higher than what we have with the continuous wave lasers. Now that we have discovered the type of lasers according to their type of emission, here are some examples of a few that are used in dental practice. This slide shows the most common and how they look like, and some of them is just what they're made of, the component. And as you can see, there is a wide variety in design simplicity. Now let's start talking about the characteristics and uses of these lasers. Starting with ruby lasers. A ruby laser is a solid-state laser that uses a synthetic ruby crystal as its medium and was previously used in ophthalmic surgery to repair retinal tears. Ruby lasers produce visible light in the range of 400 to 550 nanometers. They are transmissible by quartz fiber and absorbed strongly by melanin, which is a skin pigment. However, they have limited coagulation capabilities and allow for hemorrhage to occur, which is why they're no longer preferred in medical practice. Next, let's discuss erbium lasers. They are built with two different crystals, the EYAG or yttrium aluminium garnet crystal and the RCR-YSGG or chromium synthesized yttrium scandium gallium garnet crystal. Both of those crystals have wavelengths of 2940 and 2780 nanometers respectively. The erbium lasers are hard and soft tissues compatible and have the most FDA clearances for dental procedures. The primary chromophore is water, but hydroxyapatite absorption also occurs, but to a lesser degree. They have an excellent thermal relaxation and cause very little collateral or thermal damage in tissues when proper parameters are followed. While using these lasers in medical procedures, there is little need for anesthesia and little mechanical damage to surrounding tissues of the part being treated due to it. Now on to Nd:YAG lasers. They were the first type of true pulse lasers marketed exclusively for dental use in 1990 and consist of an invisible solid-state laser with a wavelength near infrared at 1064 nanometer. This wavelength is absorbed by pigment in the tissues, primarily hemoglobin and melanin, so the laser energy can penetrate deeply into tissues. Nd:YAG lasers have excellent biostimulative properties. They function through a 4-level laser system, which means that 4 energy levels are involved in the laser action. On to diode lasers. Diode lasers for their part are becoming quite popular due to their compact size and relative affordable pricing. They contain a specialized semiconductor that produces monochromatic light when simulated electrically. An example of a diode laser would simply be a laser pointer that you can use during like a presentation. The wavelength of diode lasers are near the infrared region and range between 805 and 1064 nanometers. Diode lasers can be used in both contact and non-contact mode, and can function with continuous or gated pulse mode. They can be used to cut or burn soft tissues, mostly. The last lasers we will discuss is CO2 lasers, and have been available in medicine since the early 17th and also been used in dentistry for more than 25 years now. Carbon dioxide lasers have a wavelength of 10,600 nanometers in the infrared region and are highly absorbed by water. Even though the name implies that CO2 is a gas in the medium, nitrogen and helium are also needed in the chamber for the medium to become active when pumped with an electrical current. CO2 lasers are very efficient and exhibit excellent hemostasis. They are mainly used for soft tissue procedures and operated as continuous wave lasers that can also be operated in gated wave mode. There is no need for searches when using CO2 lasers. To highlight what was just said, we can retain that the use of lasers has created a revolution in medical practice and dental practice as well. In dentistry, lasers can then be used in laser-assisted cavities and management, such as the diode lasers, because its wavelength causes cavity to shine. In restorative dentistry, we use area lasers to cut between tooth and bone or to cut soft tissues. And now the CO2 lasers is used in oral surgery such as frenectomy, vestibuloplasty, or alveoloplasty, where great precision is needed when you make incisions, and because CO2 lasers also have an excellent hemostasis. Lasers application does not limit to dentistry and spreads to a vast majority of fields out there. Lasers are also used in industry, for example, for welding or melting processes, for cutting or drilling holes, or to test the quality of the materials. In the military, lasers are used as weapons, or they are used to evaluate distance, velocity, and direction from distant objects. And to do that, they use a reflected signal. In telecommunication, lasers are used in fiber optic communication, holography, water communication between submarines. Last but not least, lasers are used in medicine, like previously mentioned, in the treatment of detached retinas to perform micro and bloodless surgery. They can also be used in the treatment of human and animal cancers and skin tumors. Lasers used in medicine and dentistry is mainly because of their characteristic and interaction with tissue and the biological effect they can have. The characteristic of lasers that makes them so special in medicine are absorption, because specific molecule in the tissue known as chromophore can absorb the photon lasers produce. Reflection, because laser beam can bounce off of the surface with no penetration and interaction at all, and sometimes that property is needed. Transmission, because laser energy can pass through superficial tissue to interact with the deeper one without affecting the superficial one. Finally, scattering is an important characteristic of lasers interaction with tissue, because once laser energy enters the target tissue, it diffuses in various directions, and sometimes without burning or irritating surrounding tissues, and only affecting the part that you need treatment. I hope you found this presentation helpful and edifying. Let me know if you have any question or concern that I can help clarify. Thank you for your attention and have a wonderful day.